All right, so first up on the is going to be, we have two presentations on non-destructive testing of bridge decks. First one is going to be from collaborative effort with our Office of Materials and Technology from State Highway Administration. We have Ross Cutts from Maryland State Highway Office of Technology. We also have Rodney Wynn and Dave Hollins from Maryland Environmental Science and Nicholas Gagarin from Stargrub. Please welcome up here.
All right, good afternoon. I'd like to thank the Office of Structures for allowing us this opportunity to speak with this outstanding audience today. And this panel right here, we have Ross Cutts, who works with Maryland State Highway Administration. We have David Hollins, who works with the Maryland Environmental Services. We're still trying to decide if it's a state agency or not. So
We're a state agency.
it depends, okay? And then we have Nicholas Gargan with Startup, okay? So we're going to get started. Building a GPR-based bridge deck presentation program, okay? All right, here we go. Here's the outline of the presentation that we're going to do for you this afternoon. Okay, in the past, the methodology used in the Office of Structures was the worst first. In this era of technology and data, we require methods that are efficient and repeatable. This initially started as a research project 3 years ago. We partnered with academia and the industry to determine if GPR was a viable option in Maryland State Highway Administration. After 3 years, with outstanding results and significant recognition over the country, in 2015, our Maryland State Highway Administration was nominated as one of AASHTO's top 16 projects. And then we were actually nominated and received one of the top 4 projects in Region 1. Okay, so the results have been very positive. The way that we utilize the data and the processing methods, outstanding, okay? Typically, the Office of Materials and Technology collects the data. The Field Excavation Division collects the data for the Office of Structures to utilize. In the past, we would collect data for approximately 30 to 40 bridges annually using the traditional methods, okay? In 2015, over an 8-week period of time, we utilized the GPR technology and scanned over 117 structures, okay? The cost was approximately between $10,000 to $15,000 per structure. For 2016, the target goal is 250 structures over an 8-week period of time, and the cost would be reduced to $5,000 to $7,000 per structure. Right now, we're on target to meet that goal and potentially exceed it, okay? Long term, we want to implement in the bridge program of doing approximately 300 structures per year, but not only scan, but also the process. Production level data collection allows us to significantly collect a large number of structures safer, faster, and cheaper, okay? And the technology is capable to reducing the delays not only public, but also to reduce MOT as well. Production level data processing, automated, okay? This has kind of been the glitch with using GPR in the past, is that it would take it would take a lot longer to process the data collected than it would be to actually scan it. But with an automated pipeline, we think we've resolved that issue internally, okay? So whereas we would collect, it would take one week for one structure per week, now we're doing 20 structures per week. When it would take 1 day for data collection, now it takes only 1 week for processing. Okay, and that just gives you a brief glimpse, the background of what we've done as far as the research and the history with the GPR data collection. Okay, at this time, I'd like to introduce David Hollins with Maryland Environmental Services. Thank you.
Thanks. All right. So thank you, Rodney. It's my pleasure to be here today to discuss the 3D GPR pilot project that MES has been working on for the past 2 years with the State Highway Administration. The equipment that we're using consists of a custom trailer-mounted 6-foot wide near ground penetrating ground coupled antenna array that is towed behind a standard Ford F-150 pickup truck. The antenna uses step frequencies between 150 megahertz and 3 gigahertz and obtains maximum scan resolutions at approximately 8 miles per hour. At this speed, we have high feature contrast within the scan images, which among other things is ideal for identifying rebar curves within bridge decks. GPS location mapping of scan data is accomplished using an RTK dome raised above the sightline of the work vehicle. This prevents unnecessary location distortion from the metal frame of the vehicle and the roof line of the vehicle. In addition, we're using a software package that visually shows the location of each scan pass with respect to all previous passes at that same location. Using this software, GPR collection crews can in real time accept or reject a scan pass if it does not meet minimum scan requirements such as, but not just limited to length and lane placement. Between 2015 and 2016, we have made significant improvements to our collection process. New software enhancements enable us to see scan coverage more accurately than before. This reduces repeat scans in partially completed structures, which was a problem initially. So, additional improvements focused on crew and motorist safety, which includes the use of advanced maintenance of traffic setups and lane closure permitting. At this time, with ideal conditions, we are experiencing on average 160% increase in bridge deck scan completion during any given work shift. Let's see. Our team has learned a lot of valuable lessons working on this project. Specifically, we focus on individual lanes rather than entire bridge structures. We have found that this method is more productive than focusing on individual bridges, especially when working on Maryland interstates, which it's almost impossible. This is because the travel time between scan passes can be really extensive, so it almost makes it not even worth it. Completing test runs can expose problems before they occur in the field and become difficult or impossible to fix remotely. So as part of our process, we've actually identified a control bridge that we, before each shift, will go and run a scan of to make sure that the software is working appropriately. Let's see, this can put the entire, in these problems in the past that have popped up before we did these control passes sometimes require the crew to exit the vehicle to solve the problem. And this can put the entire crew at risk of an accident. And as we have found on this project, vehicle accidents do occur. Safety is always number one priority, and as such, the crew should never exit the vehicle unless absolutely necessary to do so. Throughout this project, and that's the next part, SHA and MES have been developing a standard operating procedure that documents our collection process. Draft SOPs are available upon request from our state highway representatives. And part of the SOP is actually data analysis, which Nicholas will share more about. Thank you.
Thank you, David.
My pleasure.
So before I start talking about analysis, this is what I get from David. I get a set of files, and each file represents a scan of about 5.5 to 6 feet wide of data. And in a scan, there are about 20 lines of information. And in each line, the data is spaced at about 1.5 inches. So what I'm going to talk to you about today is it's not a training course on GPR analysis. It's just giving you an insight about how much quality control, how much automation is needed to actually get an effective result out of GPR. Traditionally, you've looked at something called a radargram, and it would take an expert to interpret it. Well, the pipeline that we produced actually interprets the information, organizes it in comprehensive data elements, and then allows you to then summarize the information into statistics for each data element that can then be used for assigning a grade to the condition of a structure. So having said that, this is a long introduction, but I'm going to be going through about 18 slides in about 6 minutes, but it's all about results and graphical results. So the main focus is about automation. When one talks about bridge deck, one talks about surface condition, concrete cover, and steel condition. If you lose steel cross-section, and we are able to actually identify and measure certain distances that are appropriate to actually give you a sense for the condition. So each rebar is actually detected individually using its synthetic aperture radar signature, and it looks like basically a bunch of hyperbolas, and that's done automatically. So looking at a typical bridge deck, it identifies about if you look at a given lane, you have 2 scans per lane for 12 feet. Then you have the shoulders, about 2 scans, then the right shoulder, then the left shoulder. So for a 4-lane highway, you're looking at about 11 scans, and that's about 500,000 automated detection of hyperbolas. So that's significant detection. So we look at the concrete surface condition, so we are able to identify any inconsistencies in the surface in terms of its material. And if one has an overlay, one can actually separate the thickness of the overlay from the concrete cover. So you can break the cover as part of the concrete and the overlay. So this is a schematic that shows you that it really takes 2 steps. The first step is a preparation of the project. So let's say you're given 300 structures to analyze. You prepare the general information, location, so on and so forth. And then you receive thousands of files. Well, the first step is to actually organize the files into a project. And then once you know that the coverage is sufficient, 80 to 90% of the surface of the bridge deck, you then go through quality control for potential external interference, and then you proceed with computing all the data elements. So the pipeline can not only identify the basic data element, but also we are adding special requests as needed, but also we can also detect utilities and near the abutments if they're buried, and we provide not only contour plots, summary tables, but also GIS ready files. As mentioned, the production rate is about 20 reports for 2 engineers per week. So, and that's most of the engineer's time is to verify that the information makes sense and meets the quality control requirements. So let's go over some illustrative results. Again, this is not intended to be a training course. This is just giving you a sense of what can be done. What I did here are organized in this next 4 slides. 2 image views of the results provided for 4 different data elements. Concrete surface condition, concrete elevation, concrete cover, and bridge deck thickness. So the top is always the first structure, the bottom is the second structure. And one can see that in the second structure for concrete surface condition, there is something going on in the middle of the deck. In terms of, if you notice, we are only plotting the area that's been surveyed. We do not do any interpolation because this is actually the true measurement. This is a surface plot of the actual measurement. Looking at surface elevation, in the second structure, one can see where potential potholes are developing, and this was a structure that was in fairly bad condition. Looking at concrete cover, the top structure shows clearly that it exceeds the 2 and 2.5 inch cover requirement, but still it takes an engineer to look at each plot and imagine if you had 300 plots like this to look at, it becomes quite overwhelming. So what we ended up doing, we ended up looking at per span across all the scans, looking at a histogram of all the values for a given data elements. And here, this is the beginning of a method to actually assign a grade to a structure. So the top left column is the first structure, the top right column is the second structure. One can see that if one can assign ranges of acceptable, marginal, and not so marginal ranges. In this case, we put green for acceptable, yellow for marginal. And one can see that for the left, the first structure, the histograms are fairly tight, and this is a newer structure, not older than, I think, 2 or 3 years. On the right-hand side, one can see the deterioration of the histogram. It's got a wider base, so looking at standard deviation and median, one could actually be able to statistically assign grades based on relevant data elements. The second set of results is qualitative. Here one can see that 5 scans were taken over an overlaid bridge deck, and here some of the defects can be observed in red, and they're localized. And because the data is so dense, we can actually define a fairly detailed map of where the local defects are. This is a close-up of span 1, span 2, and span 3. Each scan is analyzed independently and then plotted together. So there's no consistency factor assigned to each analysis. So if one looks at the bottom 2 scans that were measured fairly closely to each other, one can see the continuity of the different defects developing in the overlay. The next example is an example that shows a 2,600-foot bridge where 4 scans were taken. And this is about the results of the rebar detection and how when one does rebar detection, one gets not only a sense of how deep each rebar is, but also what the condition near the rebar is, as well as the strength of the signal. And based on that, one can then develop a sense of the condition of the rebar. So in this case, I'm going to show you for the same bridge, which had 26 sections, 3 different sections of different condition. So first is a good condition where each rebar and across each of these scans, there's 20 different measurements, 20 different GPR measurements. So it's a true three-dimensional measurement. So you can get your rebar spacing. The pipeline actually detects each rebar and computes the spacing of between each rebar. You can also notice that there are features in between the rebar that have different colors. And it's because they have different values in terms of what their natures are. And they do not, even though they are not rebar, I still plot them to show you that there are things going on around the rebar. So this is an acceptable condition. This is a condition where one can see that there are additional features showing up near the rebar. And then this is where the detection of the rebar becomes more difficult because there are too many events going on around the rebar. And again, this is the same design over the same bridge, so same analysis, and one can see this this particular section was above a waterway, and I believe that this structure may have experienced more deterioration than the previous sections. So in short, we have data collection and data processing are now linked together, and it's pretty much automated. The quality control aspects are quite significant, and they must be automated also. And in terms of the overall processing times, for for a simple structure, typical structure in highways, it takes about 8 to 12 hours of actual processing time. And then the rest is about verifying the results are correct. The reports are automatically generated and then assembled at the final stage of quality control. So if you care to have more information, technical information, please do not hesitate to ask. But I hope this gives you a sense of how much has been automated and how much is generated. Thank you very much.
Okay, so I'm actually here to close. So over the past 3 years, we have been working to develop a successful GPR-based bridge deck preservation program, and over the time, we have been awarded AASHTO's Suite 16, and we have actually seen this project start to transition from a research into potentially becoming part of our program. And we have started to produce results that are GIS based and that they can actually be trended over time. So we now have a opportunity to track trends across our network. So we are quite excited for the future, and we are grateful for the support provided by Office of Structures, the Federal Highway Administration, AASHTO, UMD, MES, and Staro Dub. Okay, great. Do we have time for questions? Or?
Do we have a couple minutes for questions? Just go ahead.
Okay. Yep. Yep.
Are you calibrating your GPR models with cores?
Yes. So part of this project has actually been to build up a large library of cores to confirm. So yes. Mm-hmm. Yep.
Yeah, I heard you talk about statistical ranking of different bridges based on the data, right?
Mm-hmm.
How are you doing that? Are you doing it just cover statistical analysis? Are you doing it the amplitude and the cover? Can you explain a little bit of how you're doing that? Are you doing a 90%, with the based on average and standard deviation, 90% minimum cover? How are you
Right.
doing that?
So that's currently kind of what we're kind of in the process of exploring, but I anticipate us probably providing in terms of all of the characteristics that we're quantifying. But as far as to providing the exact, that's kind of still part of our research. Okay.
Regarding trending, how often will you go back, and to what extent will you go back to that bridge site to establish a trend? Will it be reference bridges, for instance, or will you go to every bridge?
So I can't speak in terms of directly for Office of Structures, but I could foresee us doing something like where we would scan every structure maybe once every 3 years. If there's particular structures that we're seeing change happening faster, then we could keep track of it. But I think that that's part of what we've got to figure out. But the fact that we can now start to take readings up to high or close to highway speeds, the fact that you don't have to have that, the cost of the maintenance of traffic drops off, it becomes a lot cheaper.
Pete, we'd like to further to maybe do every 5 years, do the interstates.
Yep.
You know, I-95, I-70, do the major corridors and, you know, some of the other, you know, the major route systems and try to do a consistent, you know, every how many years. The second thing we're trying to do, to try to condense the reports into something that, you know, what's the results, is to correlate maybe what we're getting into the condition states. You know, how much of the deck is in condition state 1, how much of the deck is in condition state 2 or 3 or 4, just to give you something to summarize the data and present to someone. So that's what they're trying to work out on this group, this next grouping that they're doing this year.
So a particular interesting challenge that kind of comes up is the amount of data that you have, and trying to come up with strategic ways to present that data in a way that you can both understand it globally for the whole structure or the whole network compared to by spans. So it's kind of incredible the amount of detail that we now have, and it's trying to construct those tools for the visualization and the trending.
What's the distance from your array to the top of the deck? And did you have to sweep your decks before you actually did that work?
Yes, well, I'll let Nicholas go into the height, but as far as sweeping the decks, yes, especially for the shoulders, Maryland 100 here in Route 100 here in Maryland is completely covered in debris and junk and things like that. And metal debris can cause a lot of signal reflections and false data. So we actually work with the state highway districts to schedule street sweeping vehicles to go in, and it worked in nicely because they had their yearly plan or goals for so many bridges and structures for street sweeping. So we were able to kind of tie in with that to get them to focus on certain bridges before our scans, because we did find that there was issues when we did not have a bridge swept with some false information coming back. And then what we were at, about 4 inches, 3.5, 3 inches off the bridge deck.
But to answer your question about the offset to the ground,
Yeah.
it's a near ground coupled antenna in the sense that we've looked at the optimum height, and we determined that anything higher than 3 inches greatly reduces the amount of penetration we can have on the bridge deck. So 3 inches or lower. You're welcome.
Are you guys finding good correlation in the condition of the bridge decks from your data with that of like the human inspectors?
That's a good question. So actually very early on, we actually did, I think it was for 2 structures, we did a direct comparison between, and we actually did find them incredibly close. Something I would like to point out is that's one of those slippery slopes where you're saying, well, is one of these a gold standard? And yeah, so, but we did find very close correlation. And if you are curious, I think that was released as part of our research report, so you can actually find it. Is that it? All right, great.
All right, thank you.
Thank you.